Hello everyone, in today's video we will go through the conversion rate in a batch reactor. So a batch reactor is a reactor that has no inlet streams or outlet streams, as we discussed before. Conversion is the amount of moles reacted over the total moles. Okay, so if we use this chemical equation as an example, our reactant is A. So the conversion is how many moles of A has reacted, which is the initial amount of moles of A minus the amount of moles of A leaving, divided by the total amount of moles of A, which is the initial amount of moles of A. Okay, so we need to rearrange this conversion equation in terms of FA. FA naught, which is the initial moles of A times X, equals FA naught minus FA final. Therefore, FA final equals FA naught minus FA naught X, which is FA. If we take out FA naught as a common factor, we'll be left with 1 minus X. The same could be said in terms of concentration. Ca equals Ca naught times 1 minus X. Okay, so let's go ahead and see how the conversion is applied in a batch reactor. So we'll go ahead and start with the mole balance, which we have done before in previous videos for a batch reactor, which is input minus output plus generation equals accumulation. We can cancel out these two terms because in a batch reactor we don't have any inlet streams or outlet streams. The generation is the rate of reaction times volume equals accumulation, which is change in moles over change in time. Okay, we need to change this differential of DNA, which is the moles of A, in terms of X, because we're trying to convert our equation in terms of conversion, which is X. Therefore, we know that Ca equals moles over volume. Okay, therefore the moles equals concentration times volume. We can substitute this into our equation, our differential. Therefore, the right side will look like this: the differential of CAV. And since the volume over dt, since the volume in a batch reactor is constant and doesn't change with time, the volume can leave the differential. The left side will stay the same. So let's go ahead and take out the volume from the differential, dCA over dt, and the left side is still the same, nothing has changed. Now we can cancel these two volumes from both sides. Therefore, RA equals dCA. Now we want to change this concentration also in terms of X, and as we discussed before, that Ca equals Ca naught times 1 minus X. Ca naught. Therefore, the right side will be differential of Ca naught times 1 minus X over dt. Now the initial concentration is a constant, therefore it can also leave the differential. Now the equation will look like this after taking out the initial concentration from the differential. 1 minus x over dt. We can also take it to the other side if we want. Okay, so RA over CA naught, which is the initial concentration, equals the differential of 1 minus x over dt. Now we need to differentiate each of these terms inside the bracket separately. Okay, so differential of 1 over dt minus differential of x over dt. Differential of 1 is 0. Therefore, this term will cancel and we'll be left only with this term, which is negative dx over dt. The left side will still stay the same. RA over CA naught. Okay, now our equation will look like this. Rate of reaction over the initial concentration equals negative dx over dt. The rate of reaction for this video, let's assume that its first order rate of reaction equals negative K Ca. And it's negative because A is a reactant and it's being consumed. Let's go ahead and substitute that, which is negative K Ca over Ca naught equals dx over dt. Again, we'll change the final concentration in terms of conversion. Therefore, it'll be negative K Ca naught 1 minus x over Ca naught equals differential of x over differential of time. The Ca naught can cancel out from the left side, and we will be left with negative 1 minus x times k equals negative dx over dt. We can also eliminate the negative from both sides. Okay, now we need to rearrange this equation to have the like terms in one side. So we'll move this to the right side and the dt to the left side. Therefore, we'll be left with k dt equals 1 over 1 minus x dx. Okay, if we integrate both sides, left side has limits from 0 to t, and the right side has limits from 0 to x. We'll be left with kt equals negative ln 1 minus x. If in the problem statement you're asked to solve for t, then you can just move this k to the other side. Therefore, time equals negative ln 1 minus x over k. However, if you're asked to solve for x, you'll use this equation and you'll make both sides to the power of e to get rid of the ln, as we discussed in our previous videos of battery reactor mole balance. The right side will be e negative ln 1 minus x. The ln will cancel out. You'll be left with e to the power of kt equals negative 1 minus x. If we times the negative into the brackets, it will be negative 1 plus x and the left side will be e to the power of kt. Okay? Therefore, x equals e to the power of kt plus 1. And that is your function of x in terms of time. So that's it for this video. We discussed how conversion is in a batch reactor. For the next video, we'll see how the conversion affects the CSTR reactor. That's it for now.